Good afternoon. My name is Michael Sankur. I am a GSR. I work under Dr. Dave Auslander. I'll be talking about the Energy Information Gateway. And so the little outline is I'll be giving an introduction, the purpose of the gateway, the design, the deployment and testing, and the modifications for use in a commercial environment, in this case, Saturday Hall. So the Energy Information Gateway is being developed at UC Berkeley. It's a residential load controller and information aggregator. It communicates with dumb and smart appliances, gathers load information, and sends control commands when needed. The project is being funded by CIEE and CEC, and we are using and adapting the residential version of the Energy Information Gateway for use in the DI-ADR project. The gateway is being developed as a reference design that's completely open source, and it is a local load, it provides local load control for residents in the residential case, and it utilizes a spectrum of standards and products in the market right now. So the design of the gateway is as a communication and control system. It collects all data from all appliances connected to it, from weather, from the user. It provides supervisory control of dumb appliances and allows smart appliances to do their own control. And it also monitors the control of smart appliances. So if a fridge doesn't turn off when the gateway wants to, maybe it'll turn off the fridge. The gateway is developed in using the OSGI framework, which provides a modular framework. It uses multiple communication media to communicate with appliances. Some examples are TCP/IP, SSH, Zigbee, and UDP. It has a web-based user interface. For those of you who saw the demo upstairs, you saw that. And it also hosts a database for configuration files and historical data for analysis. Here's a reference design for the commercial energy gateway. As you can see, the gateway's in the middle, and it communicates with the occupants via a user interface. It communicates with appliances over a variety of methods, and I'll talk about that later. For the commercial case, or for Saturday Hall, we assume that the gateway will only control plug loads, and that a central controller will control HVAC and lighting. The gateway also talks to the database. The gateway's connection to the outside world is through the building energy management system. And here's how the gateway is deployed. We have the gateway in the middle, and we connect to a Raritan PDU. And the PDU is a unit with 8 controllable outlets. Each outlet has sensors to control its power use, and you can also turn them on and off. And the Raritan PDU controls dumb appliances, or legacy appliances that can't control themselves. The gateway also uses Wi-Fi or Zigbee to talk to simulated appliances, and we can simulate smart appliances over a laptop. And you can see the deployment in a sample office. We have the fan and a lamp in the top left corner of this picture, controlled by a Raritan. We have a web user interface. The gateway is just run on a desktop computer. And then we have 2 laptops which simulate smart appliances, and we can communicate with those using Wi-Fi or Zigbee. So we have done some modifications to use the residential gateway in the commercial setting. We assume that in the residential gateway, we assume that the gateway will control lighting, HVAC, and plug loads. However, in the commercial case, we say that it will only control plug loads. So we take advantage of the gateway's modular architecture, and we say that it's only responsible for plug loads. The gateway will obtain local user input from the occupants, and it sends this to a central controller. The gateway also will just only control plug loads. One modification we used is to utilize the Jade framework for networking, so that multiple gateways can talk to each other and also talk to a central controller or a central moderator. And this allows for inter-gateway negotiation and a bidding process. And if you have any questions, you should visit our website at mechatronics.berkeley.edu.